Hey guys, we're moving into circuit protection devices, switches, and series circuits. We've got a couple diagrams drawn up here. This one should look familiar. I've added a circuit protection device and a switch, but again, it's a simple series circuit. We have a power supply, conductors, a load, which is a light bulb, and our ground, which is our more conductors. We talked about having a fire if we short a wire out. We have a circuit protection device. Those can be fuses or circuit breakers. The way I remember them in the wiring diagrams, so we have circuit protection devices, we have fuses and circuit breakers. If you look at the emblem for fuse, it kind of looks like an S. Fuse has an S in it. Circuit breakers, kind of like a C if you turn it sideways, circuit breaker has a C in it. So if you look at it, it looks like an S, it's a fuse. If it looks like a C, it's a circuit breaker. So our top diagram, we have a light bulb. As we go through this, I'll refer to everything. So if you're getting confused, think of everything's a light bulb. I was once told by an older guy, everything's a light bulb. If we come down to this electric motor, if we change our mind and think, hey, it's just like a light bulb, just like that very basic circuit we saw in the last video. So we have a 2 ohm light bulb. If we go back to Ohm's law, we have 12 volts equals blank times 2 ohms. It's going to tell us this circuit will have 6 amps of current flow. Now you've noticed my fuse is a 10 amp fuse. This circuit under normal circumstances is going to flow 6 amps. If, like we did with the last diagram, if I add a wire, so let's say that wire rubbed up against something in the chassis, which is a conductor and is grounded, we ground that wire out. Now the amperage, remember, is going to go sky high. Our circuit protection device is our weak link. So rather than that whole wire catch fire and burn up, that fuse, it melts on the inside, everything's safe. Fuses are a lot easier to change than an entire wiring harness. So that fuse pops at 10 amps. Now, let's say I popped that fuse and said, man, that fuse popped, I'm going to put a big fuse in it. So I jump up to a 30 amp fuse. That fuse is not going to blow until 30 amps. The problem being that this wire will only handle 20 amps. Which one's going to burn up first? It's going to be our 20 amp wire. Fuse will be okay, it might get a little hot, but we're going to have a wiring fire before that fuse blows. So if you're ever working on something, make sure you put the proper fuse in. You can go to all data, the owner's manual will tell you what that fuse is rated at. It is our weak link there, easier to change than rewiring a vehicle, or if the vehicle even survived the fire. Our second diagram, again another series diagram. When we talk series diagram, if you follow through the path, it all goes in a row, in a series. Think of a series like a TV show. They all play out in order. So here's our series, we go through the circuit. Now you'll notice this circuit protection device is a little different. This load is a little different. This load is a electric motor, a brush type motor. I'll be loading the Google Classroom some cheat sheets on diagram emblems and stuff, what some of these symbols mean. But we've got a circuit breaker. Circuit breaker works a little different than a fuse. What they have going on inside of a circuit breaker is they've got 2 pieces of metal attached to each other. And they're 2 different types of metal, and they heat up. And as things heat up, they expand. So the one piece of metal is a different metal. As it heats, it's going to expand more, and it's going to arch. And when it arches, it breaks contact inside that circuit breaker. So it heats up, it flexes, it opens up, there's no more current flow. That unit over time will cool down, make contact again, and if there's still a short or an overload, it will break contact. Same deal here. It's a 10 amp setup, our ohms are still the same, so we have 6 amps flow through that circuit. That 10 amp breaker should not trip unless we apply a ground somewhere. A ground before the load, so now we have low resistance in the circuit. You guys will notice a switch in the circuit. This is a normally open switch, which means under normal circumstances that switch is open until somebody closes it and allows electrical flow through that circuit. Circuit breakers and switches, I consider them to be conductors. They conduct electricity through them. Switches, when they're closed, they conduct electricity through them. There shouldn't be much voltage drop in that switch or circuit breaker unless there's a problem. We talked voltage drop, that's where we had 12 volts, all the way up to the bulb, we still have 12 volts. Our drop happens is when that load uses the volts up. Now, in this circuit, let's say in this electric motor circuit, I get in here and I add some extra load in that circuit. Let's say for some reason I wired a bulb in there. And let's say that bulb is also 2 ohms. So now my total resistance in that circuit, as we flow through, we should have no resistance through our circuit protection or our switch. Here we got 2 ohms, we go through another 2 ohms. In a series circuit, these add up. We would have 4 total ohms in that circuit. So to go back to Ohm's law, we have changed our 2 to 4. And if we do the math on what times 4 equals 12, it's 3. Now this circuit's only flowing 3 amps. We've slowed the flow down. What do you think happens to our motor as we run less flow through it? It slows down. The light bulb will be a little dimmer. The motor runs a little slower, so as the amperage slows down, our outputs, our loads, are going to give us less work. This can also happen, so let's say it wasn't a light bulb. You guys know in Ohio, I despise rust and corrosion, but if we have a corrosion issue at our ground, so we have rust at that ground, and let's say I have, let's say 6 ohms of resistance at that ground, that's going to slow amperage down a lot. This motor's going to spin slow. If it's a light bulb, it's going to be dim. So as we come through this, when we get to the other side of the motor, we had 12 volts going in with our drop. Coming out, it's not going to use up all the volts because there's still volts being used at the extra resistance. And if we have our meter out, and we'll talk meters and other electrical tools later, we would show we'd show voltage on the back side of the motor because there's still voltage being used in this resistance at the ground. So these are series circuits, circuit breaker, fuse, our protection devices. We have switches to control everything on and off. Remember, fuse looks like an S for the symbol. Circuit breaker looks like AC. I will see you next time.